So now let's get started. Okay. So you can see the screen, right? Okay. So let's say the way, if you see the hello.c program, so the hello.c program is present on your hard disk. This is present on your hard disk, HD hard disk drive. And we take this program and we compile this program. No, we say gcc hello.c and it generates an executable a.out. And this a.out is also present on the hard disk. Now, when you give this program for execution, then what happens is so this is your CPU, and then this is your memory. Yeah, so the program that is present, a.out, that is present on the hard disk, it gets loaded to the RAM. What is present in the hard disk? Yeah, it is loaded. That's true. So what is present in the hard disk? It's a kind of a recipe for how to create a main memory layout of the program. It's loaded. Yeah, both. No, loading means copy from one. We call that. It's not exact copy, but no, loaded, copied. It's okay. Yeah. So loaded is a better word than copy. So what happens is the a.out that is present on the hard disk, it contains the recipe for creating what is called as a main memory layout of the program. Main memory layout. And what you're seeing on the slide here, this is what is called as a logical main memory layout. Logically, these are the sections that are present. A program that is loaded for execution, it contains what is called as a code section in which the instructions of the program from different functions are present, add, subtract, so on and so forth. And then there is what is called as a data segment. And the data segment contains memory for global variables is allocated in the data segment of the program. And then there is a section of memory where stack is located, and there is a section of memory which we call as heap, from which memory from malloc calls are allocated. We will see what are static variables in a while. So this is a logical view of the program. This is a logical view of the program. All right. So, but in yeah, it gets updated whenever, by default, it gets overwritten, not updated, it gets overwritten, replaced. Not updated, it gets overwritten whenever you compile. Procedure invocation means you call a function whenever a function gets called. That's in the old programming languages parlance, functions, procedures, they are used interchangeably. Think of procedure means function invocation. What's between heap and stack here? No, we will see. Sometimes there is nothing present, sometimes something is present. And so, but broadly speaking, these are the logical sections that are present in the main memory layout of your program. And if you actually see, in example layout, then if you go here, so now this logical, this is your whole for a when you are using a Linux operating system on an x86 64 processor, on an Intel processor, this is what is called as a this is how the memory layout of a process looks like. A program, when it is given for execution, it becomes what is called as a process, and this is how the memory layout for a process looks like. So you can see that part of the process memory layout, it contains space for the instructions and data structures associated with operating system. This kernel memory means the operating system instructions and data structures is what is present in that space. And then if you see here, you have below the lower addresses BIOS. And BIOS is usually realized using ROM or flash RAM. So it contains a micro loader which loads grub or other bootloader that is present, which in turn loads operating system, so on and so forth. And you can see there is a read-only segment which consists of different kinds of sections. Text section is nothing but the section which consists of the instructions of the program. And RO data section is what is called as a read-only data section. And then there is a data section which consists of memory, which allocates where memory for global variables is allocated. And then there is a stack here. And this user stack, this is a place where memory for local variables is allocated. And there is this heap which grows at the opposite direction of the stack. And this is where memory that we get through malloc. When we make malloc, memory comes from this space, from this heap space. And so the stack and heap grow in opposite direction. In between some segment of opposite means their stack is growing, memory you keep allocating. As more memory is required, you keep expanding this way. But heap is expanding in the opposite direction. So heap, we try to get memory by expanding it upwards. Stack, we get the memory by expanding it downwards, because these are higher memory addresses, higher memory addresses, lower memory addresses. So when you write a program, recursive program, kernel memory is the place where operating system resides, because it's important. Kernel memory, so operating system does lots of things for you. If you have listened to that printf, the discussion on printf and scanf, when you call printf, what happens? What will happen when we do printf? See, you forgot. Write system call will be called. So write system call, the code for write system call is present here. The code for, it's not part of your program. It is present here. Okay, so you keep executing your program, your instructions are present here. And when somewhere you hit a printf, then what happens is control will transfer to some place in the kernel where the code for write system call is present. And after the write system call is executed, then again you come back to the place after the printf. You understand what is happening? Okay. So when there is a problem, Printf is in the code region, that is .text is the code region. But printf in turn calls write system call, and write system call is part of the kernel memory. We cannot say printf is a control transfer statement. Printf is it's a function. These system calls are unique to C or the same for all. BRK for the time being ignore. I also have to see, but it essentially is used to expand the memory that is associated with heap. So system calls are it's an interesting thing. Systems of calls are independent of the language actually. System calls, Yash has a very good question. System calls are independent of the language. The write system call, it will have some number, like number 32 or something like that. So when you want to call the write system call, you have to call, let's say, for example, you may have to execute an assembly language instruction such as int32. Okay. Or there will be some other instruction, assembly language instruction called as syscall32 or something like that. So the system calls are independent of the programming languages. Okay. Very good question, Yash. Okay, so now, yeah, this is, so when you write code, recursive code, where the base case is not properly done, then function keeps on calling it again and again and again and again. So the stack keeps on growing. And when it tries to override this read-only memory mapped region of shared libraries, you get a segmentation fault. Or if it is not there, it will try to overwrite heap memory or data section or read-only segment, something like that it will do, and the system crashes. So this memory layout, good question, Mitansh. So this memory layout it's not the same for all the operating systems. So the memory layout of a process on Linux operating system is different from the memory layout of a process on a Windows operating system. So this is dependent on the operating system. It is dependent on the processor that is being used. Okay, so are you all with me here? Printf is in read-only memory means instructions of the program are not modified. Text section contains, once the program is loaded, you cannot override the instructions of the program. So that is the reason why it is in the read-only segment. Once it is loaded, you cannot modify. Okay, so far so good. Do you get some big picture on what's happening? This is how the process looks like when it is in action. A program looks like. A program in action is called as process, and what you are seeing on the screen, it is called as the main memory layout of the process. Well, you may get the doubt here. From this main memory layout, the whole memory seems to be allocated to only one process, but there are several processes that are running on your system, right? So what's the deal? Function calls are control transfer, but the function call involves control transfer. It is physically, good question, Stayesh. It is physically possible to modify it, but OS places restriction. But whereas the bottom part where it is ROM or flash RAM, it is not physically possible to override it. Okay. So this is an alternate picture of the same. So you can see this is text segment. This is the place where instructions of the program are present. In this space, instructions of the program are present. And here we have a data segment where the data for global variables is allocated. And then here this OS is present. And then there is a stack which grows here, and then there is a heap which grows here. And then there is a place for shared libraries. I have to reshare the screen. It's not visible, or the screen is not visible? It is visible. So this is an alternate picture. One thing I would like you to do here is understand here is, so there is what is called as a buffer overflow problem. So in order to counter buffer overflow problem, counter buffer overflow problem, the base address of the stack is randomized a bit. So because of that, the memory for local variables in every program execution, it changes slightly. Okay, you can see this random stack offset to counter buffer overflow problem. I will post one reading material on this, but we cannot get into the details as it is beyond the scope of this course. Randomized means, it will start, like for example, the base address of the stack, when you execute one time, it could be 1000. Next time when we execute, it could be 1040, something like that. So within some range, it will start the base address. In order to understand at a very high level, this randomization is done to solve a security problem called as buffer overflow problem. Okay, so that much you should understand. Okay, and beyond that, we cannot get into the details. It requires a lot more big detour to get there. But I'll post some good reading resources on this. So those of you who are inclined, you can read. Okay, but the problem here is, so well, if the whole memory is allocated to one process, but you can see on your computer, there are many processes running. How is memory allocated to all these processes? You understand the problem? If you look at this picture, the whole 4 GB of memory is allocated to one process. But if you see your activity monitor, or if you use stop or PS, or then you see many processes running. Okay. So in reality, what this is what is called as a virtual address memory layout. This is not a physical memory allocation. So in practice, what happens is, like, for example, in your system, there are two processes that are running. One is a Chrome process, and then the other is your program. So both are coexisting, or let's say, one could be your program, other could be Visual Studio Code. So if you see the memory layout for Chrome thinks that the whole process is there for itself. The whole process, the whole memory is there for itself. Similarly, when your program also thinks that that the whole of the memory is available for itself. But what happens is, this memory layout that you are seeing, this is a virtual memory layout, whereas this is the actual physical RAM. So what happens is, a chunk of the virtual memory here, you can see this part of the virtual memory is allocated this part of the physical memory. And similarly, this part of the virtual memory is allocated this part of the physical memory. This part of the virtual memory of process B2 is allocated this part of the physical memory in the physical RAM. So if you see, you can, this chunk is allocated to process P2, this chunk is allocated to process P2, and this chunk is allocated to process P1. So in the actual physical RAM, what happens is different processes, the memories for different processes coexist. But from a process layout, okay, but from a process, from a single process perspective, Chrome thinks that the whole memory is available for itself. Your program thinks that the whole memory is available for itself. And let's say your program is a small program and it doesn't require this memory space at all. Then this memory, then this virtual memory is not allocated any physical memory at all. Okay. Are you all with me here? And one interesting thing here is the operating system kernel. The OS kernel is present here, right? So the OS kernel is present here. And both of them, they could be allocated the same, the OS memory from both. The OS, the memory that is associated from OS in both the processes, they get mapped to the same space in a physical RAM. And so what happens is you will study more about this whole idea. So when they no, so I don't know exactly how. Okay, so I'll take Abhinav's question in a minute. So this is what happens in practice. This is what happens in practice. Okay, so there is a page table. There are data structures called as page tables, which map a physical virtual memory to a physical memory. And you'll study about a whole lot of these things in your operating systems course. Okay, this is just a kind of some peek into what is happening under the hood. So Abhinav's question, how can memory management apps say I clean this much RAM? It is, think of it like this, okay, virtual memory, it's a logical view, it's just a logical view, but when you try to access your data that is present here, you use, let's say the address of the data that is present is 1000, you try to access the data at 1000, but this is present somewhere here in the memory. So internally this 1000 gets mapped to some other address 3000. You go and access the data from 3000. This is what happens. So when I'm not sure about the Android apps, but the task manager tells you how much of this physical RAM is occupied by different processes. Like how much of physical RAM is occupied by process P2, like for example, this could be 100 MB, this could be 200 MB. So process P2 to overall it is occupying 300 MB. And it is possible for your task manager has, so you'll understand why you need virtual memory, because it's a very clean way of, you think that everything is available for you, but internally it is managed for you. Because otherwise, when you are writing a program, you need to know where your program should be located in the physical memory. And there are lots of challenges are present. But instead, you just think that everything is available for you, but there's an internal translation mechanism which maps these pages, your virtual pages to physical pages. Virtual memory really doesn't exist. That's why it's called as virtual. Yeah. And also there are other reasons like, there are lots of holes. You get many nice properties. These two processes are completely isolated with each other. Like for example, one simple thing, let's say process P2, there is a bug in process P2 and process P2 stacks keep growing and it comes and overrides process P1. If they are just allocated memory in the physical memory, then what happens is, these processes, they interfere with each other and you get into lots of troubles. And the operating system kind of nicely solve this problem by isolating the address space of one process from some other process. Anyway, so, you study all these things in your next semester in detail. I'm just giving you some sneak peek into what is going to come. The important idea is this. Why we are bringing up all these issues is, if you go back, this is the logical view of the memory layout of your process. Are you with me? This one, first one. This is a logical layout. The second, from here, when we move here, this will be the actual physical layout. And when you look at the second actual physical layout, this is the point 2. There is a natural question that comes to you, that is, hey, the whole memory seems to be allocated to me, but there are other processes running on the machine. How about them? And the answer to that question is, the view that you get is only a virtual memory view, but there's an internal mapping of the virtual memory to physical memory. And that's how the whole thing is managed. Okay, this is the story. Point 1, logical memory layout of the program. Point 2, virtual memory layout of the program. Point 3, that the physical memory layout of the program is actually realized due by having a mapping between virtual memory layout with physical memory. Okay. So now, if you are fine with this, okay, let's do one thing. So, okay, so okay, so now I'm not doing anything. Let's keep this as it is. So pi is allocated memory, yes or no? It is allocated memory. Radius is also allocated memory. Okay, let's first I will show two things for you and then we will see. So now what do we say? Printf enter radius. Perimeter. To pi r. To mean. I'm going to make it void mean. Okay. Where are we? Oh, okay. We are in 21A. Okay. So GCC vmem.c. %. Okay, so we got the perimeter. So now let's use this thing, GCC minus S vmem.c. So what will minus S do? Minus S, it will generate the assembly code associated with this. So one important thing I would like you to keep in mind. I don't want this one, how to, great. Let's keep this. Here. Okay, this is better. Anyway, so now if you see vmem.c, well, the assembly code associated with vmem.c. So there are set of instructions. There is a section in the assembly code which is called as data section, which starts from line 4 and goes till line 9. And line 7 tells us that pi, the variable pi, it requires 4 bytes of memory and it needs to be initialized to some value. You are seeing some string there, but it is equivalent to the floating point representation of 3.14, I guess. So this is the data section. This is the data section. So anything that is there in the data section, anything that is there in the data section, so it will anything that is there in the data section in the assembly code, it goes to the read-only, it goes to this part. So pi is allocated memory here. And this is the instruction that is given in the, we are looking at the assembly code now, but if you look at the equivalent a.out file also, it tells the loader that it has to create a data section and it has to allocate 4 bytes of memory in the data section and it needs to be initialized with something. Okay. Are you with me here? The first idea, how the recipe is specified in the hard disk. Does it make sense? And then after that, you see there is one more section called maybe this, whatever this object, I don't know. So maybe I'm not sure. Okay, so good point, good catch, Dalno. And then we have a read-only section .ro data, which allocates memory for the 3 strings that we are, 3 string literals that we are using in the program. The first string literal is enter radius string, %f perimeter. All these 3 string literals, they are allocated memory in this read-only data. And when the program is up for execution in the read-only data section segment of this, the memory for these 3 strings is allocated. Are you with me here in the second part? Okay, how string literals are allocated memory in the main memory layout of the program. And this is how they are specified in the RO data section. And then there is this text section where the actual instructions of the program are present. This is the text. This is the whole text section in which the The instructions of the program are present and they are loaded into this text section. Okay. So, and then there is a stack, there is a radius. Radius is a local variable. It is allocated memory on the activation record associated with main, but there is no explicit allocation of memory for stack. It's automatically, you just initialize the stack pointer and that's it. Okay, so memory for radius is allocated on the stack and it will be allocated when the function main is activated. All right. Are you with me here so far? Or like, for example, if you see, if you have something like float compute area, there is a function which takes float r float area is equal to area is equal to pi times r and return area. Okay, so now let's compile this program and see what happens. Patience, guys, patience. I'll tell everything. So now you see there is vmem.c. In the vmem.c, you have compute area, and then if you see, if you go look at compute area is also a function here, and the memory for the local variable area, it is allocated on the activation record associated with the compute area when compute area function is invoked. So if you go look at this code, you don't see there is no memories allocated for area or the radius variables in the activation in the data section. You only see the memory for pi is in the data section, only memory for pi is allocated. And then no, the memory for these things, no, these string literals, they are allocated in the read-only section. And the memory for these local variables, they are allocated on the stack in the activation record associated with that function when we invoke that function. So this is what is happening. What is the difference between macro is never allocated a memory? Macro is never allocated memory. Muskan, so in the exam you would have done it wrong. So I thought it's just I just wanted to give one more option in the exam, but you are ending up making mistakes. What is a macro variable? Read, Mano. We discussed about it quite a bit. Didn't we discuss about it, guys? In the class, we looked at, we compiled it using CPP. We looked at the code, how the macro variables are replaced with the corresponding values. Yes or no? Yeah, hash defined ones. In fact, we have used hash define pi 3.14 or something like that. Okay. So now the important, interesting thing here is the first thing I want you to understand, what is the lifetime of the variable pi? Where is memory for variable pi allocated? Where is memory for the variable pi allocated? In the data section. And the data section will be there throughout the program execution. Hence, the lifetime of the variable pi. What is the lifetime of the variable pi? Lifetime. When is it born and when does it die? When is it born? And so pi is born when it's when the program execution starts, and it dies when the program execution ends. It's like pi is born with the universe, and it dies at Mahapralaya at the end. When the whole program vanishes, then it's gone. Okay. That is the lifetime of pi. All global variables, they are allocated, their lifetime is throughout program execution. Lifetime of pi, whole program execution. Sad story, everything eventually comes to an end. Okay. I think it's good. Otherwise, it is, everything coming to an end is good. No? So anyway, let's not get there. So this class has to come to an end. Otherwise, you'll get hungry. Okay. My frustration has to come to an end. That's good. Your frustration on me has to come to an end. That's good. So it's good. Anyway, so and how about area, memory for area? When will compute area, this variable area in compute area function, when will it come to life? When is it born? And when does it die? When compute area is called, then area variable is born, and it is allocated memory in the activation record associated with the compute area. And R also, variable R also. And when we come out of it, I want you to kind of, did we write some, and we have looked at the recursive functions where multiple area variables are active at the simultaneously. Yes or no? Okay, so it is possible that two different versions of area are active at the same time. But the important point is, this area is born when you call this function compute area, and it ends when we come out of it. Okay. So the lifetime of it is program activation time. No, function activation duration. Only when the function is active, then area is also alive. Are you with me on this one? Second point. And so this is about the lifetime of a local variable and the lifetime of a global variable. The second important point is the scope. What is the scope of the variable area? Where can you use it? We can use it only within the function. What is the scope of the variable pi? It is the whole program, the whole code. So here we have to be a bit careful. Like for example, here, if I take this out and put it here and compile, what do you think we will get? GCC vmem.c. You will get a error because pi is not defined here. So the scope of the variable global variable pi is after it is defined in anywhere in the file. Okay, are you with me here? Okay. Similarly, like for example, let's say, and defining global variables in the middle of the program, it's very bad idea. We should not do that. So now when you, do you think you'll get an error or? When we compile, okay, again you get an error because area is available within function compute area after its declaration. Okay, so it has to be here. So now let's say, for the time being, let's comment out this code. For int I is equal to 0, I less than 5, plus I, printf the area of this circle with the radius %d is %f /n I compute area %f for, I'm just using radius as I is a integer, right? So I declared I as an integer. So now I compile a program and I ran it. This is what I get. Okay. What happens here? So no Anika. So what happens here when we call compute area with an integer I? Why? What happens? Tell me. No, sorry, but what happens? So the integer I gets typecasted to float, implicit typecast. There's an implicit typecast to a floating point number. Okay, to float. Great. So what is the scope of the variable I? What is the scope of the variable I? It is only inside the loop. So now let's say I want to count the number of times this function is called. Static int count is equal to 0. And so plus count printf compute area called for %d times. Not static. No, static only, you know. Count. No, it will increase. So compile this program now. So you see that the variable count, it is retaining its value across function invocations. Are you with me here? Count initially is 0, and then when we called it, it got incremented by 1, again it got incremented by 1, so on and so forth. So is it possible for count to be allocated memory on the stack? Count is a local variable, right? Is it possible for count to be allocated memory on the stack? It's not possible, because if it is allocated memory on the stack, then it has to be popped out. So count has to be allocated memory in the data section of the program, because data section remains the same. It's never deleted. Are you with me here? So memory for count is allocated. Memory for count is allocated not on stack, although it's a local variable, but in global data section. So the question for you is, what is the scope of the variable count? What is the scope of the variable count? The scope of the variable count is compute area. But what is its lifetime? Scope is within compute area. But lifetime is the whole program execution time. Are you with me here on this one? Lifetime program execution time. Yeah, before a program starts execution, memory for global variables is allocated. Now, what we are saying is the variable count, it is when we use that thing static, it retains its values across program function invocation. Because whatever that is there in area variable, for example, next time when we call compute area, it will not be there. It will not be there. That is for a different reason, no? So a variable is visible only after its declaration, no? So that's the reason. So we want count to be visible. We want the value of count to retain after multiple program invocations, not after across function invocations. So it has to be allocated memory not on the stack, but in the global data section. It will always show 0. If it's not static, then every time it enters, it is, it will always print 1. That's true, Ramandeep. If it's not static, it will always print. So let's run this program. You see, it always shows 1 because every time we enter into compute area, a new version of count is created. But when we put static across invocations, the same count is kept. Are you all with me here? Yes, no, maybe? So now the story, Now let's have a question for you. What is the lifetime of the variable of memory that is allocated using malloc? What is the lifetime of the memory that is allocated using malloc? Until it is freed, until we call a function free to release it, its lifetime is there. Are you with me here? And is there any scope for it? Is there any scope for the memory that is allocated using malloc? There is no scope. You can, as long as you have the address of that base address of the memory chunk, you can use it anywhere. Okay. I hope in today's class, we introduced 2 very important ideas. One is scope, lifetime. We looked at local variables. Among local variables, we have 2 kinds of local variables, non-static or regular static or static. And then we have global variables. And then we have memory that is allocated through malloc and freed using free function. So we usually don't talk about scope of memory allocated through malloc, but in order to make it, I want to make a conceptual point. That is the memory that is allocated through malloc. We can use it anywhere in the program until it is freed. Are you with me here? Yes or no? I want to make one important point here. Now, the memory that is allocated through malloc, it is available throughout, Karthik. So until you free it, it is available, and you can use as long as you have the base address of that memory, you can use it. Page file is out of the scope for today's class, Rohan. We'll study it again in operating systems. So, yeah, so this is, are you all with me on the ideas discussed so far? And I want to make one interesting point. Static doesn't mean it's not moving, Pranjalis. Static doesn't, that's not what static means. You are kind of applying English language semantics to it. Static doesn't mean it's not moving. Static means it's, when we access a text file, the entire file gets loaded in the memory. Good question. Yes, it's a very complicated answer. It's not, we'll take it up in a different class. I want to show one thing before we, couple of things I want to show. One thing definitely we will see, the next thing we will see depending upon hunger level we will decide. So I am using two screens here, two bash shells, gcc -g vmem.c, gdb a.out, and break main, and print address of pi. Okay, so I'm running two versions of the program here. I'm running two versions of the program. So gdb a.out. So I'm running two processes. I'm running two processes in one terminal. Sorry. In one terminal, break run main pre. So where are we? So we are AP. Why source code is not available? Oh, you didn't. A0 control F GCC GDB a.out break main run. Okay. This is in terminal 0, guys. Okay. This is in terminal 0. Now let's go to terminal 1, and I am running the same thing again. Break main UI enable run. Okay. So in terminal 0, I am running this process. On terminal 1, also I am running this process. Print address of pi here. Print address of pi. You can see in both the terminals, the address of pi is the same. Are you able to see? Are you with me here? Are you able to see the observation? Right now we are at terminal 1. The address of pi is this. And if you go here and when we look at the address of pi in terminal 0, it is showing the same address. Are you all with me here? Yes, no, maybe. Same address. How is it possible that same address is allocated for two different processes? Or you are hungry? It has got nothing to do with global data section. Because the memory that you are seeing here, it is a virtual address. The actual physical location at which the pi in one process is present and the pi in the other process is present, they are different physical locations. So there are these two processes that are running now. So this is process P1 and this is process P2. Okay. So there is pi here. The address of pi in both the processes is just exactly the same. They are both present in their own data section. But this is virtual memory and this is physical memory. This pi gets mapped to one address and this pi gets mapped to a different address. Are you with me here? Yes, no, maybe. Do you understand what I'm trying to say? No, not for processor. It is a complete, we don't want process P1 and P2 to interfere with each other. In this particular case, the recipe that we use it for generating these two processes is the same. It has got nothing to do with global variable and local variable, but there is something to do with the local variable though. The reason is printf address of radius here. Where, okay, next. Print address. Why? Oh. No radius in this code. On line 21, there is radius, right? You know what happened? Why it's not there? No, it's not commented. See, optimized out. No, because we declared radius and we didn't use it. So compiler thought it's a useless variable and we removed it. So it's optimized out. So this is what is called as a dead variable elimination technique. Okay, so anyway, so let's say at least if you try to get the address of variable I, I is not, see, everything is acting super smart today to my frustration. So local variables, there is the virtual address of local variables can vary slightly because the base address of the stack is randomized. Are you with me? Anyway, so let's take a step back. Are you all with me at least on this point? Global variables, the pi here and here, they have the same virtual address. No, the 8010, this is a virtual address, this is a virtual address, but the physical addresses are different. Yes or no on one? Why virtual address is the same, Manusha, means, you know, when you wrote the recipe, that's how you have written it. You can say that the virtual address is the same because both of them are generated from the same a dot out. This and this, so they are generated from the same a dot out. Yes or no? That is one answer. So when they are generated from the same a dot out, why do you think, you know, pi should have a different address in one process, but from its address in a different process? Does it make sense? Then why not for local variables? Because for local variables, recall our discussion. So compiler does some randomization in order to solve the buffer overflow problem. It does some randomization of the base address to solve the buffer overflow problem. Because of that, local variables. No, Anand. Local variables and pi, they are the different for both the programs. That's not the reason. No, heap memory is not like, it's not random. Count will also have same values in both programs. These two are two different things. They don't have any relationship between them at all. See, it is like this, okay? Let me put it this way. You using the same recipe, you are playing drama in two different places, so both of them got the same name. Okay, but they don't have the same values, okay? Like for example, if you feed, if you serve this guy pizza, this pie pizza, if you serve, this guy won't be fed. Okay. Relative location is the same. That's a good question. Whenever I see Shyam's last name, so there is in math, there is something called as Krylov subspaces. So I feel like, that if you just kind of change those order of some of the characters of Shaivam, then we get Krylov subspaces. So I tend to read it like that. Okay. I think we should take a break, guys. Everyone will is hungry. I am also hungry today. Is it possible to address pointer to a specific address? Yes, it is possible, Akshat. It is possible. And in fact, when you do embedded systems programming, you do a lot of hard coding of addresses to pointers. Tell what, Rohan? Krylov subspace. I also don't know. It's a, I just, it's a in math, there is something Krylov subspace. Yeah. See, I will share it with you. This is what I'm talking about. So whenever I see Shaivam's name, I see this Krylov subspace comes to my mind. But nothing to do with what we are talking about here. That's all. What's special in lunch today? So today I came to office after a long time so that I can teach you guys properly. So I have